Hello, welcome to Engineers Mindset. Now, let's say we have this beam on the board and we are asked to do the shear force and bending moment analysis for the beam. Now, the very first thing you will do, like always I will say, is to determine the reactions at the supports, support A and support B. Okay, so that means we have to start by first of all outlining the free body diagram. Okay, so I will have F BD, which is free body diagram. So I'll bring back the beam. So at point A, I recognize that we have a pin at this point. This is a pin support. And for a pin support, we have two reactions, one vertical and one horizontal, okay, at that point. So we simply have one vertical reaction. So we call this simply RAY, and we have a horizontal reaction at that point called this RAX. So this is simply at point A. At point B, we have a ruler, and for a ruler support, we just have one reaction normal to the surface. So this reaction is actually vertical, so it's just a single reaction for a ruler. So simply call this RBY. This is point C. Now, between A and B, there is a uniformly distributed load whose intensity is given as W. Okay, so in order for us to be able to determine these reactions, RAY, RAX, and RBY, we have to convert the UDL to point load. And I said that to convert a UDL to point load, simply multiply the value of the UDL, that's the intensity of the UDL, to the length covered by the UDL. In this case, the length of the UDL is simply what given as L. That's the entire length from point A to point B. That's the length of the UDL. The intensity of the UDL itself is simply what? W. So for us to convert this to point load, I have to multiply the intensity, that's W, by the length, L. Okay, so that means the load becomes W times L, which is simply WL. Now, after converting this to point load, you now have to place this point load on the beam. And I said that to place the UDL point load, place it at the middle of the length covered by the UDL. So since the length of the UDL is simply the entire length of the beam, that's from A to B, which is simply here L, it means the middle of L is simply what? L over 2. That is where this UDL load will be. Okay, so first of all, I will convert this UDL to point load simply by multiplying W to L. So I'll have WL as a point load. Then it has to be at the middle of the length. Therefore, middle of the length is somewhere around here. So I have the point load WL. This becomes the point load of the UDL. So from point A to the point of the load is simply what? L all over 2, because I have to divide the length by 2 to place the point load. So from the point load to point B is also what? L all over 2. So I have this. Okay. Now the next thing to do is to simply employ equilibrium equation. And from equilibrium equation, recall, I said that summation of forces in the x-axis is simply equal to 0. That simply means sum all the force in the horizontal direction and equate them to 0. Okay, so a careful look at this beam shows that there is only one force pointing in the horizontal direction, which is the x-axis now, and that force is simply RAX. So this simply implies that RAX is equal to 0. So the reaction in the horizontal direction at point A is actually equal to 0. Next equilibrium equation is simply summation of vertical force is equal to 0. So we consider vertically upward force as positive, meanwhile vertically downward force as negative. So you sum all the vertical forces and equate them to 0. Taking note, all the forces pointing upward should be considered as positive, while forces pointing downward should be considered as negative. So if I do that, I will simply have RAY is pointing upward, so it's positive. RBY is pointing upward, so it's positive. So I will simply have, okay, so I will simply have RAY pointing upward, so it's positive. I have WL pointing downward, so it's negative. Simply minus WL. Okay, I have RBY pointing upward, so it's positive, plus RBY. And according to the law, the whole of this force is equal to 0. So I have this. Now, having obtained this, I can simply send minus WL over to this side of the equation. So I will simply have that RAY plus RBY is now equal to, if I send minus WL over here, it becomes positive. Negative sign crosses an equal to sign becomes positive. So I'll simply have WL. So call this equation 1. Now, equation 1 happens to be what? A single equation having two unknowns, ray and rby. So which makes it very impossible for us to solve. Now, the only way we can make a break for this is by simply what? Considering another equilibrium equation, which means take moment about a point. And from equilibrium law, the summation of the entire moment about a particular point on a beam is equal to 0. And I always say, if you're taking moment about any point on the beam, you take moment about the point where you have numerous of forces, because moment is simply force times distance. If you take moment about a point, it means there's no distance between that force and the point. Therefore, it becomes that force times 0. So you take moment about the point where you have numerous of force on the beam. And of course, I have two reactions at point A, two unknown reactions, RAX and RAY at point A. So it's wise for me to take moment about point A, so that the moment of this force RAY about that point is 0, because there's no distance between this reaction RAY to that point. Also, the moment of RAX to that point is also 0, because there's no distance between this force and the point. Okay, so we take moment about point A. Take moment about A, and recall summation of moments about point A is simply equal to 0. Let's consider clockwise moment to have to be positive and anti-clockwise moment to be negative. So we'll work with that rule or that direction. So simply like I said, the moment of these two forces now, RAY and RAS about point A automatically becomes 0. I have to now take moment of these other two forces about that point. So the moment of this load, WL, about point A, simply this force is pointing downwards. So it will turn in this direction. It turns all the way from this point to this point, which means it goes in this direction. And this is clockwise to our assumed direction. We said let clockwise moment be positive. Since it is clockwise, then that means the moment of this force about point A is positive. Also, since moment is force times distance it takes this force to get to point A is simply what? L over 2, because it moves from there to this point. Simply L over 2. That's the length it takes from this point to point A. So I'll simply have WL times L all over 2. That gives us the moment of this force about point A. Next moment to take is moment from point B, sorry. This is point B. Sorry about that, okay? So next moment is moment of point B about point A. All right, so if I take moment of this force about point A, this force is pointing upwards. So which means it goes all the way in this direction. This is the line of action of the force is going upwards. So the moment to go all the way in this direction. And if you notice, this is negative, which is anti-clockwise to our direction. So which means the moment of this force about point A is negative. And the distance it takes this force to get to point A is simply the entire length of the beam, which is L. That is moving from point B down to point A. You have L over 2 plus L over 2, which simply is L. Okay, so, and it's negative because it's anti-clockwise. So you simply have minus RBY times L, and this is equal to 0. Okay, so you may wish to send minus RBY over to the side of the equation. I will simply have WL into L over 2 is now equal to RBY times L. So from here, it's easy. L can actually strike L. Okay, L can actually strike L, or you may wish to divide both sides by L. So it means on this side, what I'm left, it is simply WL all over 2 to be equal to RBY. So it means that the reaction at point B, the reaction of the support at point B is simply WL all over 2. This gives us the reaction of the support at point B. So this unknown is found, RBY. So if we know this reaction at the support, all we need to do is simply take this reaction and substitute into what? Equation 1 to obtain the value of what? RAY. If we do that, we are simply going to have that from 1, okay, from equation 1, we had that RAY plus RBY is equal to WL. We had this in equation 1. Okay, so we now have RAY, okay, RAY plus. Now, in place of RBY, we've already obtained the value of RBY to be simply WL all over 2. So putting that value there plus WL all over 2 is now equal to simply WL. So you have WL. Okay, so to make RAY subject, we'll have to simply send WL over 2 over to this side of the equation. So we simply have RAY is now equal to WL minus WL all over 2. Of course, WL minus WL all over 2 is simply like saying 1 minus 1 over 2, because this is WL and this is WL over 2. It's just like saying 1 minus 1 over 2, and that will simply give you what? 1 over 2. So which means this reaction at point A is also WL all over 2. So we've gotten the two reactions, the two unknown reactions. The next thing to do is to simply substitute this reaction back to the original beam in place of the support. We'll find the reaction for the support at point A, we'll find the reaction for the support at point B. All we need to do is to place back these reactions at these supports and then work with the original beam to do the shear force and bending moment analysis. Okay. All right, so at point A, we obtain the reaction at this point, and we obtain that reaction simply RAY. We obtain it to be WL all over 2. Also at point B, we obtain that support reaction to be, that's RBY equals WL all over 2. So you substitute it directly to the original because of the UDL. Now the essence of this is that for us to be able to do the shear force and bending moment analysis, we have to form what is called a shear force equation and a bending moment equation, because on these equations lies the point of maximum bending moment and the point of contraflexion. So that is why we have to impute them back into the original beam and then carry out the shear force analysis. So let's start the shear force analysis now. Shear force analysis. Okay. So I always say that shear force is simply the stepwise summation of the entire force acting on the beam from the beginning of the beam to the end of the beam at each point of the beam. Now we consider upward forces to be positive and downward forces to be negative. Okay. Okay, so we always start from beginning of the beam. So at point A, that's the beginning of the beam, shear force at that point simply means the force that exists at point A. If that force is upwards, then it's positive. But if the force is downwards, then that force is negative. All right, so we simply have shear force at A. So we'll use SFA. S means shear, F means force, A simply means at point A. And that's equal to, so the force we have at point A is WL over 2. And this force is pointing upward, so it's positive. I'll simply have WL all over 2. That's the shear force at A. Now, between A, the next point is B. But between A and point B, there is what? A uniformly distributed load. Between A and point B, there is a UDL. So because of this UDL, we have to take what is called a section. That section is what helps us to obtain the shear force equation. So since the UDL is across the entire length of the beam, you have to take a section. So you consider a section XX at a distance of X from point A along AB. So somewhere along AB, you're simply taking a section, let's say somewhere around here, XX, and you're simply saying, let the distance from point A to the point of section remains X meters. Okay, so distance from point A to the point of section is simply X meters. This now means that the UDL portion or the length of the UDL about the point of section, which is simply length from point A to the point of section, which is from this point to this point, is simply what? X meters. That becomes the length of the UDL about that point of section. So remember always, to convert a UDL to a point load, you simply multiply the value of the UDL to what? The length covered. So if the length now is X meters, the length about the point of section is X meters, it means to convert this UDL to point load, simply what? Multiply the value of UDL, which is W, by the length. The length now is X, so it becomes W times X. That gives us an equation. Okay, now before we do that, this becomes shear force along AB. So shear force AB, which means we are moving from point A somewhere along AB, we encountered a UDL. So always bring down the final shear force or the previous shear force in the first step, which is at point A. Bring it down, you have WL all over 2, because it was this shear force that moved and then encountered a UDL along AB. Okay, so this is now minus. Remember, for a UDL, of course, it can be seen here, the load of UDL is always acting downwards. So that's why you must always remember, if the load is acting downward, shear force for that particular load is negative, or that force is negative. So we have minus. So since the length from point A to the point of section, the length of the UDL about that point is x meters, it simply means to convert this UDL to point load now, I will simply have W times x. This becomes the point load, where x is the length about the point of section. All right, so if I have this now the intention is actually to take shear force at point B, but the essence of this is to obtain what is called the shear force equation. This equation helps us to determine the point of maximum bending moment on the beam. All right. Now, so finally, at B, that is to say, when this length finally runs from point A down to point B, at B, the value of the length x is equal to the total length of the beam, which is L. At B, that is from point A down to point B, x becomes L, because remember, x runs from point A along AB. So if it finally runs down towards point B, it becomes the total length of the beam from point A to point B, which was given to us as simply L. So at B, x equals L, which is the length of the beam. So therefore, this becomes shear force at B prime. Now, we are using shear force at B prime because at point B, there's an upward force of WL over 2. So we are not involving it yet in the calculation. So we'll simply say shear force B prime, which means initially at point B. Okay, so the shear force is simply equal to, we have WL all over 2 minus. So if you put in x to the L, in place of this x, you simply put in what? L. So it becomes minus WL. You have this. So of course, these two can subtract. You have WL over 2 minus WL. This is simply saying half minus 1, because WL over 2 is like saying half, 1 over 2 minus 1. Okay. And so WL over 2 minus WL will simply give us shear force B prime, which means initially at point B, the shear force is simply minus WL all over 2. Okay. Okay, so that gives us the initial shear force at point B. But on getting to point B, this force now, called the shear force B prime prime, okay, on getting to point B, this force minus WL all over 2, which is this shear force initially, now encounters an upward force of what? WL over 2 at point B. So we simply say finally at point B. So shear force B prime prime simply means finally at point B. This shear force now encounters an upward force of WL over 2. And remember, if the force is upward, it's definitely going to be what? Positive. All right, so we simply have plus WL all over 2. Therefore, finally at point B, shear force B prime prime is simply minus WL over 2 plus WL over 2 will simply give us 0. So we have this. So take note, at the end of every shear force analysis, you must always obtain 0 as the answer. Okay, so we have that. Okay, so we can now start the bending moment analysis. Bending moment analysis. Bending moment analysis. Okay, so as always, the moment of force about every point is 0. So the moment of this force about point A, I said moment is force times distance. So if I'm considering point A, there's no distance between WL over 2, which is the force at point A, and this point A. So it means the distance is 0 because this force is directly at point A. So the moment of this force becomes WL over 2 times 0. So that is why it's always moment about a point of every force is always 0. So the moment at point A is equal to 0. So you have this. Okay. Next is to take moment at point B, but because there's a UDL on top of the beam, like always, you have to take section. So we took section from point A down to the point of section somewhere along AB. Consider a section XX at a distance X from point A along AB. So we're simply saying from A to this point, any point around AB should be what? Called X. That's the section. Okay, so if that's the case, then it means the moment of forces about this point, first thing first, this force RWL over 2, okay, of course, will have a moment about that point. This force WL over 2 will have a moment about that point, and distance it takes this force to get to that point is simply what? Still x meters, because this force is really at point A, and distance from point A to the point of section is still x. So that means moment, since we are now out along AB, becomes moment along AB, and that's simply equal to, now the moment of this force WL over 2 about that point still remains WL all over 2 times what? X. That is distance it takes this force to get to what? The point of section. Also, between A to the point of section, there's a UDL. So because of that, we also what? Take moment of the UDL load. Please take note, when taking moment, consider upward force. When doing bending moment analysis, consider upward forces to have positive bending moment. Meanwhile, downward forces to have negative bending moment. It's still the same thing when you say clockwise or anti-clockwise, it's still the same thing. Okay, so since I know first of all this UDL load will act downward, so it's going to be what? Negative. And then again, I have to convert the UDL to point load because moment is force times distance. So the point load due to the UDL will simply give me what? W times X. This is the point load and not moment. This is just a force. W times X is simply a force. Okay, so now after converting a UDL to point load, I always say place this UDL at the middle of the length. So let's say this is point A, okay, and this is the point of the section XX, and distance from point A to the point of section, like we said, is simply X meters. And we want to convert this UDL now. UDL that runs from point A to the point of section to point load, it becomes simply what? W times X. This is the point load. And I said if you're placing the point load on a beam, you place it at the middle of the length covered. So if the length covered is X, middle of X is simply somewhere around here, we have this load, WX. This is the point load. So which means from this point to the point load is simply X all over 2. Also from the point load to this other end, that's the point of section, is simply also X all over 2. So if I want to now take moment of this load, which is WX, about the point of section, it has to be WS times distance it takes this force to get to the point of section. And that distance is simply what? X over 2. So which means after converting to point load, I will simply multiply by what? X all over 2, which is the length it takes the UDL point load to get to the point of section. So we simply have this. All right, so at B, X as always remains what? The entire length of the beam. At point B, X equals, that is when X runs from point A down to B, it becomes the entire length of the beam. X equals L. So therefore, we now have moment at point B, and that's equal to, we have WL all over 2 times, in place of this X now we simply have L, okay, minus, this is W, in place of X we'll have L, times, we have, in place of X here we also have L all over 2, okay. Okay, so moment at B is now equal to, of course, here you have WL over 2 times L. L times L gives us L squared. So we simply have WL squared all over 2 minus. Same thing happens here. You have WL times L over 2. L times L gives us L squared. We still have minus WL squared all over 2. And of course, WL squared over 2 minus WL squared over 2 simply gives us 0. So moment at point B is equal to 0. So as always, at the end of every bending moment analysis, you must always obtain 0 as the answer. Okay, so we have that. So next thing now is to plot the shear force diagram and the bending moment diagram. So let's do that now and see. Okay, so before we plot the diagrams, I will have to, let me pull out the shear force equation along AB somewhere. Let me keep it somewhere because I'm going to need much later. Okay, shear force AB equals WL over 2 minus WX. Okay, minus WX. All right. Okay, so to draw the shear force and bending moment diagram, we trace down all the points. So we have point A, trace it down, and you have point B also, trace point B down. Okay, all right. So shear force at A. Okay, shear force at A. Please don't forget. You may wish to go back and check. Shear force at A simply gave us WL all over 2. So we'll put that down. Let's call here WL over 2 is positive. So now shear force B prime, which is initially at point B, we have minus WL over 2. So before you get to the negative values, first of all, you have the 0 mark. So this is the 0 mark, okay, which is the origin. So here is 0. Everything above the origin is positive. Everything below the origin is negative. So shear force B prime is minus WL over 2. So we simply have here minus WL all over 2. We have negative value, so it should be there, minus WL over 2. Okay. So after obtaining the points, the next thing is to trace them out. So you trace out these points, trace these points out. Okay. So you can now start picking up the shear force. Shear force at point A is WL over 2. This is line A. This is WL over 2. This is where they meet. You simply what? Connect. Asterisk. Next is shear force B prime, which means initially at point B. And initially at point B, we have that force to be minus WL over 2. This is negative WL over 2 line. This is initial, this is line B, initial at point B. So this is where they meet initially, you asterisk. And then finally, shear force B prime prime gave us 0. This is 0 mark. This is also line B. You simply what? Asterisk. So I've always said, please do well to look up all my videos on shear force and bending moment analysis for proper understanding. Okay, so I've always said the shear force diagram for a point load, because WL over 2 is simply a point load at point A. It's simply a point load. And the shear force diagram for a point load is simply a straight line connecting the point load. So from the origin, we have a straight line connecting the point load. Now, between A and B was what? It is a UDL. Between A and B is a UDL. So we simply connect from A initially, we have a UDL down to point B initially. And then finally, the shear force at B is simply 0. So from B, we connect. So we'll have the 0. So this gives us the shear force diagram. Okay, so you might asterisk. So this is the shear force diagram. Shear force diagram. Okay, so we'll do the same thing for the bending moment. All right, we pick out the bending moment values. Moment at point A is 0. Moment at point B is also 0. So that means all we have is just what? A 0 line. So this is 0. Okay. Moment at point A is 0. So you simply asterisk. Let me take this down a bit. Let me take it down a bit. Okay. So this is 0 line. Moment at point A is 0. This is line A. And this is 0 mark. This is where they meet. You simply what? Asterisk. Moment at point B is also 0. This is line B. This is where they meet. You simply what? Asterisk. You have this. So I also said in my previous videos, the bending moment diagram for a UDL is simply what? A curve. Meanwhile, the shear force diagram for a UDL is a slant line. That's why you have this slant line from point A down to point B, because you have a UDL from point A down to point B. The shear force diagram for a UDL is simply a slant line. Okay, so bending moment diagram for a UDL is simply a curve. So you simply have something like this down to point A. Okay, down to point A. So this is the shear force. This is the bending moment diagram, sorry. All right, so this is the bending moment diagram. So you have this. Okay, so that's the shear force diagram, and that's how the bending moment diagram looks like. Okay, so possible questions that could come out is you could be asked to find the point of maximum bending moment and the point of contraflexion, if possible. Okay, those are possible questions that you could expect. Now, to find the point of maximum bending moment, the point of maximum bending moment is that point where shear force changes sign from positive to negative. Okay, so we see that shear force changes sign here. This is positive and this is negative. So it changes sign from positive to negative between A and B. So it's always between A and B. Okay, so since it's between A and B, we look for the shear force equation between A and B and equate that equation to 0. Find the value of X. That value of X becomes the point of maximum bending moment. Okay, so I put that down here. The shear force equation between A and B is simply given as this. Sorry, is simply given as this, which is WL over 2 minus W times X. So we equate this equation to 0 at the point of maximum bending moment. Okay, let's do that and see. So I simply said at the point of maximum bending moment, shear force AB is equal to 0. So the whole of this value is simply equal to 0. We now have WL all over 2 minus WX is equal to 0. So all we need to do is simply what? Send minus WX over to this side of the equation. We simply have WL all over 2 is simply negative sign plus an equal to sign gives us positive. So we simply have WX. So from here, W can actually strike W. This implies that X is equal to L all over 2. This value is what we call the point of maximum bending moment. So maximum bending moment occurs when x is equal to L all over 2. That's the point of maximum bending moment. Okay. So the point where shear force changes sign from positive to negative is the point of maximum bending moment. Get the equation at that point and equate to 0. Find the value of x. That becomes the point of maximum bending moment. Okay. And maybe equation could also come, find the point of contraflexion. And of course, on this beam, there is no point of contraflexion. The point of contraflexion is simply the point where bending moment changes sign from positive to negative. So if you look at the bending moment diagram here, it's all in positive. It didn't change sign anywhere. So the point of contraflexion is actually what? 0 for this particular question. Point of contraflexion is 0. All right, guys. I hope you enjoyed that wonderful question on shear force and bending moment. All right, guys. I hope you enjoyed that wonderful question on shear force and bending moment analysis. Please, if you do, I would like to hear your thoughts in the comment section. And of course, don't fail to subscribe if you're new to the channel. I will see you in the next video with more and more wonderful questions on shear force and bending moment analysis. Thanks, guys, and cheers.